In this video, we're going to focus on finding the domain and range of a function. We're going to find it from a graph, from linear quadratic equations, equations that have square roots, rational functions with fractions, logarithmic, and exponential equations. So let's go ahead and begin. So let's say if we have a function that looks like this. How would you find the domain and range for this function? So this value is 3. Over here, let's say this is about -3. And this is 4. And approximately -4. My graph is not perfect. So when you're looking for the domain, you need to find all the possible values of x that the function has. And for the range, that includes all the possible y values that the function contain. So what do you think the domain for this function is? So for the domain, you view it from left to right. What's the lowest x value? And what's the highest? The lowest x value for the function is -3, and the highest is 3. So therefore, the domain is from -3 to 3. So notice that I have parentheses at the -3, but I have a bracket at +3. Whenever you have a closed circle, you need to use a bracket. But if you have an open circle, make sure you use a parentheses. So now let's focus on the range. The range includes all the possible y values that the function can have. So what's the lowest y value and what's the highest? Notice that the lowest is -4 and the highest is 4 if we view it from the bottom to the top. So therefore, the range is going to be -4 to 4. So at -4, we don't have an open circle. It includes -4. And the same is true for 4. That's why we have a bracket instead of parentheses. So let's try another example. So what is the domain and range for this function? Feel free to pause the video and try this example yourself. So let's start with the domain. What is the lowest possible x value that we have in this function? So notice that we have an arrow instead of a closed circle. This arrow continues to go to the left. It goes all the way to -infinity. And this arrow, it goes up, but it also goes to the right. So x can be anything from -infinity to infinity. And x can even be 2, because at this point, x equals 2. So because x can be all real numbers, it's going to be from -infinity to infinity. Now what about the range? So now let's focus on the y values. What's the lowest y value that you see on this graph? Notice that the lowest y value is at -3. And the highest y value is +infinity because it keeps going up forever. However, notice that there's a break at 2 and it continues at 4. So between 2 and 4, there are no y values. So to write the range, it's going to be the lowest y value, which includes -3, and so it goes up from -3 to 2. and it doesn't include 2, so we're going to use parentheses for that. And then union, it continues at 4 again, and it goes all the way to infinity, but it includes 4, so we need a bracket at 4, and it goes all the way to infinity. So as you can see, it starts at -3, stops at 2. There's nothing between 2 and 4, and then it starts back at 4 and goes up to infinity. And that's the way you want to see it when you're looking at the range. If you want to find the range, focus on the y values. If you want to find the domain, focus on the x values. Let's try another example. Okay, so for this function, go ahead, or for this graph, go ahead and write the domain and range for this particular graph that you see. Feel free to pause the video and see if you can get the answer. So let's start with the domain. So let's focus on the x values. So notice that we have an arrow on the left. That means it's going to keep going down, but as it goes down, it slowly moves to the left. So this graph can go to the left forever. So the lowest x value, therefore, is -infinity. Now, we really don't have a break at -3 because x can equal -3, not on this graph, but on this curve because we have a closed circle. So we don't need to remove -3 from the domain because it includes -3. Now the next jump that we see is between 1 and 3. Notice that there's no x values between 1 and 3. The curve, there's no red line between those 2 points, so we need to remove that section from the domain. And now we have an arrow that goes to the right, so therefore the highest x value is infinity, and the lowest is -infinity. So the domain is going to start from -infinity all the way to 1, because x could be anything from -infinity to 1. And then union, we have to start back at 3 because there's nothing between 1 and 3. So union 3 all the way to infinity. So that's the domain for this function. So now let's focus on the range. The lowest y value is -infinity because the graph keeps going down forever. Now even though there's a break between these two curves, we don't have a break between the y values. In this curve, y can be -2, and it can be -2 in this curve. So y could be anything from -infinity to 1. Now, between 3 and 1, if you notice, there's nothing between 3 and 1. There's no red line, there's no curve between 1 and 3 in terms of y values. So that means that for the range, we need to start from -infinity and stop at 1. Then we need to continue from 1 and stop at the highest point. The highest y value is approximately 5. So therefore, the range is going to be -infinity to 1. Now, it includes 1 because we have a closed circle. And then so we need a bracket since we have a closed circle. And then union, now it starts back at 3, but we have an open circle at 3. So we're going to need a parentheses around the 3. And then it stops at 5. Now, there's no open circle here, so it includes 5. And so that's the range for this particular function. Let's try another example. Let's say if we have a vertical asymptote at x equals 2. And in addition, we have a horizontal asymptote at y equals -1. And we have a graph that looks like this. And another one, or another curve that looks like that. But it never touches the asymptotes. So, with this type of graph, how would you write the domain and range for it? So go ahead, take a minute and see if you can get the answer. So let's start with the domain. So as we can see, the function goes all the way to the left. So therefore, the lowest x value is -infinity. As we view it from left to right, we can see that the highest x value is +infinity. But notice that the curve, it never touches x equals 2. It never touches the line. So therefore, we need to remove this x value from the domain. So the domain is going to be -infinity to 2 because it doesn't include 2. And then union 2 to infinity. So x could be anything from -infinity to 2, but not 2 itself. And it could be anything above 2 to infinity. So now let's find the range for this graph. So let's focus on the y values. Let's view it from bottom to top. So the lowest y value is -infinity because this graph keeps going down. And the highest is infinity. However, the curve will never touch the horizontal line. So therefore, we need to remove the horizontal line or the horizontal asymptote from the range because y will never be -1. So the range is going to be -infinity to -1 union -1 to infinity. So if you have horizontal and vertical asymptotes where the graph never touches those asymptotes, for the domain, remove the vertical asymptote. And for the range, make sure you remove the horizontal asymptote. Now, it's not that bad to figure out the domain and range from a graph. But sometimes you're not given a graph. Most of the times, you have an equation. So let's say if you have the equation y is equal to 3x plus 2. How can you figure out the domain and range from this graph? So for linear equations, it turns out that the domain and range is all real numbers. X could be anything and y could be anything. Whenever you have a polynomial, if the leading coefficient is 1, the range could be anything. And for all polynomials, the domain is -infinity to infinity. So let's graph the function. So this is a linear equation in slope-intercept form. Y is equal to mx plus b. The slope is 3. The y-intercept is 2. So let's plot the y-intercept first at 2. And the slope is 3, which means it's 3 over 1. So using rise over run, we need to go up 3 units and 1 unit to the right. So therefore, the next point will be here. And so we can connect these 2 points with a line. So the graph looks something like this. As you can see, it goes all the way down to -infinity and all the way up to infinity with no breaks in between. That's why we can say the range is from -infinity to infinity. Now, as it goes down, it also moves to the left. And it goes to the left forever. So the lowest x value is -infinity, and the highest is +infinity because as it goes up, it also moves to the right. And so that's why we can see the domain is negative infinity to infinity. Now what about a quadratic function, such as y is equal to x squared plus 2x minus 8? What is the domain and range for this function? Now anytime you have a polynomial, be it x to the first power x squared, x cubed, if there's no fractions and if there's no radicals with an even index number, or no absolute value, no logs, no exponential equations, if it's simply a polynomial, the domain will always be negative infinity to infinity, because there's no restrictions on the x value. X can be anything. However, if the leading coefficient is even, then the range will be limited. The range will not be negative infinity to infinity. But if the leading coefficient is odd, typically the range can be anything. So if it's like x to the first power, which we covered that example, or x cubed, the range could be negative infinity to infinity. And you'll see that as we go through a few examples. So let's go ahead and graph this function. How would you graph y equals x squared plus 2x plus 8? So because it's positive x squared, the parent function looks like this. One of the best ways to solve it, or to graph it, is to find the x-intercepts, if possible. So let's set it equal to 0, and let's factor it. What two numbers multiply to negative 8, but add to positive 2? This is going to be positive 4 and negative 2. 4 times negative 2 is negative 8, but 4 plus negative 2, that adds up to positive 2. So to factor, it's going to be x plus 4 times x minus 2. So the x-intercepts are negative 4 and 2. You need to set each factor equal to 0. So if you set x plus 4 equal to 0, and if you subtract 4 from both sides, x is negative 4. And if you set x minus 2 equal to 0, and if you add 2 to both sides to solve for x, x is plus 2. So those are the x-intercepts for this particular function. So if we plot the x-intercepts, we have one at 2 and another at negative 4. Now the vertex, the x-coordinate of the vertex, is going to be the midpoint, or the average, of negative 4 and 2. The midpoint between negative 4 and 2 is negative 1. If you average those numbers, if you add them up and divide by 2, you should get negative 1. Negative 4 plus 2 is negative 2. Negative 2 divided by 2 is negative 1. So that's where the vertex is. That's the axis of symmetry. It's at x equals negative 1. Now you can also find the x-coordinate of the vertex by using this equation. X is equal to negative b over 2a. A is the number in front of x squared, which is 1. B is the number in front of x, which is 2. And C is negative 8. So it's going to be negative 2 divided by 2 times 1. So negative 2 over 2, that's going to be equal to negative 1, which we have that. So now you have two ways that you can use to figure out the x-coordinate of the vertex. Now once you have that, we need to find the y value. So let's plug in negative 1 into the equation. Now let's substitute negative 1 for x. So negative 1 squared plus 2 times negative 1 minus 8. Negative 1 squared, that's negative 1 times negative 1. That's positive 1. 2 times negative 1, that's negative 2 minus 8. So we have negative 1 minus 8, which is negative 9. Now, it turns out I need more points on this graph, so let's say that negative 9 is somewhere in the bottom. So at this point, we can draw a rough sketch. So our graph is going to look something like this. So now we can figure out the domain and range. So let's focus on the domain. All the way to the left we have negative infinity. As the graph goes up, it's going to go to the left. And so it can keep going to the left forever. And all the way to the right, we have positive infinity. There's no breaks in between. So that's why we could say x could be anything. The domain is negative infinity to infinity. But now let's focus on the range. Because we have a quadratic function, because it's a parabola, you can see that we have a minimum. The lowest y value is negative 9. It's the x coordinate of the vertex. If you have a positive x squared function. If it's positive x squared, you have a minimum value because it opens upward. If it's negative x squared, you're going to have a maximum value because it opens downward. So the lowest y value is negative 9. And then the function keeps going up forever. So it's positive infinity. So if you have a polynomial where the leading coefficient is even, typically your range has limitations. It's not going to be from negative infinity to infinity. So the range, the lowest y value is negative 9, and the highest y value is infinity. And for infinity, you should always put a parentheses next to it, never a bracket. We have a bracket for negative 9 because it includes negative 9. So this is the range, and this is the domain. Now let's say if you want to graph an equation in vertex form. Let's say it's negative x plus 2 squared minus 1. How would you graph it? So in vertex form, we have the generic equation ax minus h squared plus k. The vertex is h comma k. So notice that h changes from, we have negative h and h here. So we need to flip the sign. Here we have positive k and positive k. We don't need to change the sign. So what's the vertex of this equation? So since we have an x plus 2 inside the parentheses, it's going to be negative 2 and comma negative 1. So that's the coordinate of the vertex. So it's somewhere over here. And because we have a negative in front of the function, because a is negative, we know it's going to open downward. So at this point, we can draw a rough sketch. So the graph is going to look like this. So for any polynomial function, the domain is always going to be negative infinity to infinity. But now let's focus on the range. The lowest y value is negative infinity, but the highest is the y coordinate of the vertex. It's negative 1. So therefore, the range is negative infinity to negative 1. And that's all you got to do for this problem. So what about this function? Y is equal to x minus 2 raised to the third plus 1. What is the domain and range for this function? So let's start with the parent function x cubed. The parent function looks like this. It's always increasing. And this is positive x cubed. Negative x cubed looks like this. The end behavior is up and then it's down. That's up, then down. So for both of these functions, you can see that the domain is all real numbers. X could be anything. And for y, the lowest y value is negative infinity and the highest is infinity. So the range is negative infinity to infinity. So whenever you have if the leading coefficient is odd, the range is always going to be negative infinity to infinity for the most part. And if you have a polynomial function, this is typically what the domain will be. So now let's graph the function with the transformation. So because we see x minus 2 on the inside, if you set that equal to 0, you'll get x is equal to 2. So it's going to shift 2 units to the right. And we have a plus 1 on the outside, so it's going to go up 1 unit. And so the graph is going to look like this. But as you can see, the domain is still negative infinity to infinity. It can go all the way to the left and all the way to the right. And as you can see, the range, the lowest y value, is negative infinity and the highest is infinity. So if you were to get, let's say, some polynomial function, x to the fifth plus 4x cubed minus 6x plus 8, you don't need to graph it. If it's a polynomial function, the domain will always be negative infinity to infinity. Now, for the range, the leading coefficient is x to the 5. So if you look at the end behavior of the graph, when it's odd, if it's positive and odd, the end behavior is going to be like this. Towards the end, it's going to be increasing, and on the left side is decreasing. So we don't know what's going to happen in the middle, but you can see that the range is going to be negative infinity to infinity if it's odd. So whenever you have a positive even function, the end behavior is up and up. If it's negative, it's down, down. So the range has limitations for these. You have to graph it to figure out what the range is. But if it's odd, the range will be everything. If it's negative and odd, it's up, down. But the range will be negative infinity to infinity if the leading coefficient has an odd exponent. Now, what about the square root of x? What is the domain and range for this function? So if you were to graph the square root of x, it looks like this. Now you need to understand the other transformations as well. Negative square root x, it reflects over the x-axis, and so it looks like this. And square root negative x, it reflects over the y-axis, so it looks like this. And finally, negative square root negative x, it looks like that. So the domain for the square root of x is from 0 to infinity, but it includes 0. The range, the lowest y value is 0, the highest y value is infinity. So the range is also 0 to infinity. But now if we focus on this function, the domain is different. The lowest x value is negative infinity, but it stops at 0. So the domain is negative infinity to 0. Now the range, we can see that the lowest y value is negative infinity, the highest is 0. So the range is also negative infinity to 0. Now what about for negative square root x? What's the domain and range? For the domain, you can see that the lowest x value is 0, the highest is infinity. Therefore, the domain is from 0 to infinity. Now the range, the lowest y value is negative infinity, but the highest is 0. So the range is going to be negative infinity to 0. Now there's something else that I want to mention with those four graphs. So let's start back with this one. Y is equal to positive square root positive x. So notice that x is positive and y, which we'll associate it with the blue sign, that's positive as well. When x and y are positive, it's going to go towards quadrant 1, because in quadrant 1, both x and y are positive. In this example, x is negative, but y is positive. So x is negative towards the left. Y is positive as you go up. So this graph is going to go towards quadrant 2, where x is negative and y is positive. As you can see, it reflects over the y-axis. If x and y are both negative, then it's going to go towards quadrant 3. So it's going to look like this. And if y is negative and x is positive, when x is positive, you need to go to the right. But if y is negative, you need to go down. So that's in quadrant 4. So this graph is going to go this way. So let's say if you have the function y is equal to the square root of x minus 2 plus 1. And you want to find the domain and range. To find the domain of a radical function, most of the time you could set the inside equal to or greater than 0. So x is going to be equal to or greater than 2. Or you can graph it. So you can see that it shifts 2 units to the left and up 1. So it's going to start at 2, 1. Now x is positive and y is positive, so it's going to go towards quadrant 1. So it's going to go this way. Now this is enough to figure out what the domain and range will be. We can see that the lowest x value is 2 and the highest is infinity. The lowest y value is 1 and the highest is infinity. So therefore the domain is from 2 to infinity and it includes 2. The range is 1 to infinity and it includes 1. So it might be easier to draw a rough sketch and then you can easily see what the domain and range will be. Or you can set the inside equal to 0 and solve for x. So you can see that x is equal to or greater than 2, which we can see that in the domain. X is not less than 2. Now what about this function? Y is equal to, let's say, 5 minus radical x plus 3. So how would you graph this function using the transformations? So if you set the inside equal to or greater than 0, you'll see that x has to be greater than negative 3. So it's going to shift 3 units to the left. That's where it's going to start. And we have a positive 5 on the outside. So it's going to go up 5 units. So it's going to start here at negative 3, 5. Now, in which direction will the graph go? Because that's going to be important to figure out the domain and range. Is it going to go towards quadrant 1, towards quadrant 2, towards quadrant 3, or towards quadrant 4? So we can see that we have a positive sign in front of x, but a negative sign in front of the radical. So we're going to treat this as if we have a positive x value, that means it's going to go to the right, and a negative y value, that means it's going to go down. So it's going to go towards quadrant 4, because x is positive, y is negative in quadrant 4. So to draw a rough graph or a rough sketch, it's going to look something like this. Our sketch doesn't have to be perfect. We just need to know where the first point is and what direction it's going. And that's all we need to basically find the domain and range. That's what we're focused on in this video. So the lowest x value, you can see it's negative 3, and it goes to infinity, which we could see that from this expression. X is equal to or greater than negative 3. So therefore the domain, it includes negative 3, and it goes to infinity. Now for the range, the lowest y value is negative infinity, because as this curve goes to the right, it's still decreasing. And so over time, it's going to get smaller and smaller and smaller. So it's going to go down to negative infinity. Now the highest y value is basically this number. So the highest y value is 5. So the range is from negative infinity, and it stops at 5, but it includes 5. So we need a bracket. Let's try one more example. Y is equal to 2 minus the square root of 4 minus x. So let's discuss the transformations. Does it shift to the right or to the left? And does it shift up or down? Well, to figure out if it's going to shift to the left or to the right, set the inside equal to or greater than 0 and solve for x. So if we subtract 4 from both sides, negative x is greater than or equal to negative 4. And if we divide both sides by negative 1, x is going to be less than or equal to 4. So keep in mind, whenever you multiply or divide by a negative number, the sign of the inequality must be reversed. So the graph is going to shift 4 units to the right. But the fact that x has to be less than or equal to 4 tells us that it won't be going to the right, but it will be going to the left. So it can either go towards quadrant 2 or towards quadrant 3, because x has to be less than or equal to 4. So we won't get this graph or this one. Now, there's a plus 2 on the outside, so it's going to shift up 2 units. So the graph is going to start at 4, 2. Now let's figure out the direction. So we have a negative sign in front of x and a negative in front of the radical. So negative x, negative y. X and y are negative towards quadrant 3. So it's going to go in this general direction. So now we can figure out the domain and range. So for the domain, the lowest x value is negative infinity and the highest is 4. So it's from negative infinity to negative 4, including negative 4. Now for the range, this function will continue to decrease as we move to the left. So the lowest y value is negative infinity, but the highest is 2. So the range is from negative infinity to 2. And so that's what you can do for that one. So now let's review a few things with radicals. So as we can see, you can quickly find the domain by setting the inside equal to or greater than 0, because you cannot have a negative number inside a radical. This doesn't equal a real number, it equals an imaginary number, 2i. Keep in mind, I is the square root of negative 1. So whenever you're looking for the domain, set the inside equal to or greater than 0. So here we can see that x is equal to or greater than 1. So the domain is going to be from 1 to infinity. Because you can only have positive numbers inside a radical if the index number is even, which if you don't see a number, it's 2. Now to find a range, this number on the outside, it's important. If it's not there, it's going to start, or it's going to have 0. But if it's there, the range is going to include 2. So because we have positive x and positive y, we know the function is increasing. So therefore, the lowest y value has to be 2 and the highest is infinity. So we could just say it's 2 from infinity. Now sometimes you may get a graph that looks like this. So the highest value will be 2, the lowest would be negative infinity. And for such a graph, the range will be negative infinity to 2. But it still has the 2. So that 2 should be somewhere in the range. That's why you need to know what direction the graph is going. Is it increasing or decreasing? Now sometimes you might have a radical with an odd index number. Let's say the cube root of x plus 1. The cube root of x function, it looks like this. So because you have an odd index number, the domain could be anything, because you can have the cube root of an odd number is a real number, it's negative 2. The cube root of positive 8 is positive 2. So you could take the cube root of positive and negative numbers. The square root of 25 is 5, but the square root of negative 25, that's an imaginary number, it's 5i. So that's why you can't take the square root of negative numbers. It doesn't give a real solution. And so that's why if you have an even index number, the domain and range will be restricted. But if it's odd, the domain and range will be all real numbers, negative infinity to infinity. So let's say if we want to find the domain for the cube root of x plus 1 minus 4. To graph it, it's going to shift 1 unit to the left and down 4. So the starting point should be somewhere over here. But it's going to have the same generic shape. So it's going to look something like this. As you can see, the domain is still negative infinity to infinity, and the range, the lowest y value, is negative infinity, and the highest is positive infinity. So anytime you have a cube root, or the fifth root, or the seventh root, the domain and range will be all real numbers. There's no restriction. It's when you have an even index number. That's when you have to be careful. Now, what about this function? X squared plus 2x minus 15. What is the domain and range for that function? So since we have a quadratic expression within a radical, you need to factor it. What two numbers multiply to negative 15 but add to positive 2? This is 5 and negative 3. 5 times negative 3 is negative 15, but 5 plus negative 3 is positive 2. So we can rewrite it as x plus 5 and x minus 3. So notice that there's two numbers that can be equal to 0. We need to set the inside equal to or greater than 0. So we have two critical points, positive 3 and negative 5. When you have more than one critical point, you need to test the values on a number line. And your goal is to find out when it's positive, because we can't have any negative numbers in a square root when the index number is even. So our critical points are negative 5 and 3. So we're going to put a closed circle at these points because these points are included. If you plug in 3 or negative 5, you're going to get the square root of 0, which y is 0 at that case. So it includes those numbers. We have to exclude the numbers that are negative. So let's pick a number that's greater than 3. So let's plug in 4 into x plus 5, x minus 3. 4 plus 5 is a positive number, and 4 minus 3 is a positive number. A positive number times a positive number is a positive number. So it's going to be positive in this section. Now, if we plug in a number between negative 5 and 3, is it going to be positive or negative? Let's try 0. 0 plus 5 is positive. 0 minus 3 is negative. A positive times a negative is a negative. Therefore, x cannot be between negative 5 and 3 because it's negative. We can't have any negative numbers inside a square root. Now, let's try a number less than negative 5. Let's try negative 6. Negative 6 plus 5 is a negative number. Negative 6 minus 3 is a negative. Two negatives, when multiplied, turn into a positive. So x can be anything between negative infinity to negative 5, and it can be between 3 to infinity. And so that's the domain for this function. It's negative infinity to negative 5, union 3 to infinity. Now what about the range? Notice that we have a positive sign outside of the square root. Now when you take a square root of a number, it's always going to be positive. The only way you can get a negative answer is if you have a negative on the outside. Since it's positive, the graph y will never be less than 0. It has to be greater than 0. So it's always going to be increasing. Now if we draw a rough sketch for this graph, the 2 points of interest are at negative 5 and 3. You can type this in a graphing calculator if you want. And if you don't have one, just type in online graphing calculator in Google and plug in this equation. So at 3, y is 0, and at negative 5, y is 0. So as x grows from 3, the function will be increasing. First, it's going to look like a square root function, and then eventually it's going to look like y equals x. So it's going to look like that. Now, between negative 5 and negative infinity, it's positive, so it's above the x-axis. As you move towards negative infinity, it's also going to be increasing as you go to the left. As you go to the right, it's really decreasing. But as you go to the left, it's going to look like this, it's increasing. So that's how this function is going to look like. So as you can see, the domain is from negative infinity to negative 5. That's the first part of the function, and then 3 to infinity. Now the range, the lowest y value is 0. The highest, it goes up to infinity. And so that's the range. Typically, the range is going to be 0 to infinity or negative infinity to 0 if you don't have a number outside of the square root. Now, let's say if we had a number outside. Let's say if it was like plus 4. So then the range will become 4 to infinity. You simply have to add 4 to it. It's going to be shifted up 4 units. But since we don't have that, it's just 0 to infinity for this particular example. So now let's move on into rational functions. So for these functions, you have a fraction. What is the domain and range for that function? What we're going to do is we're going to graph it. Now keep in mind, for this function, you need to look out for horizontal and vertical asymptotes. You need to remove the vertical asymptote from the domain and remove the horizontal asymptote for the range. To find the vertical asymptote, set the denominator equal to 0. So the vertical asymptote is x is equal to 2. Now keep in mind, the actual curve will never touch the vertical asymptote. So even though this is the equation of the vertical asymptote, x itself will never equal 2. Because if you plug in positive 2 into the equation, you're going to get a 0 on the bottom. And whenever you have a 0 in the denominator of a fraction, it's undefined. So x does not equal positive 2, which is the vertical asymptote x equals 2. Now what about the horizontal asymptote? How can we figure that part? So if you want to find the horizontal asymptote, you need to determine if the rational function, if it's top heavy, bottom heavy, or if it's the same. Notice that it's bottom heavy. The degree of the denominator is higher than that of the numerator. So therefore, the horizontal asymptote is y is equal to 0. That's just for that part alone. So if we didn't have the 1, the horizontal asymptote would be y is equal to 0. But since we add 1 to the function, it's going to be 0 plus 1. So therefore, the horizontal asymptote is y is equal to 1. So now let's go ahead and graph it. Now you need to know the parent function, 1 over x. The parent function looks like this. And negative 1 over x, which is going to represent the blue line, it reflects about the origin. So the blue part is negative 1 over x, the red part is 1 over x. This graph that we have here is similar to positive 1 over x, not negative 1 over x. So if we were to graph it, the first thing we should put is the vertical asymptote, which is at 2, and the horizontal asymptote, which is at 1. And so the graph is going to look like this. Now, what is the domain and range for this function now that we have the graph? So we can see that the lowest x value is negative infinity, and then it stops at 2 because we need to remove the vertical asymptote, and the highest x value is positive infinity. Therefore, the domain is negative infinity to 2, union 2 to infinity. Since x cannot equal 2, we shouldn't have a bracket on 2. It should be a parentheses. Now for the range, we need to remove the horizontal asymptote, which is y is equal to 1. The lowest y value is negative infinity, the highest is infinity. But y will never be 1, it's never going to touch the horizontal asymptote. So the range is negative infinity to 1, union 1 to infinity. Now what if you have a rational function but with a square root? Let's say 1 over square root x plus 3. How would you graph it? So to find the vertical asymptote, it's going to be the same. X plus 3 cannot equal 0. Or we'll set it to 0. So the vertical asymptote is negative 3. In addition to that, we can't have a negative number inside a radical. So x plus 3 has to be greater than 0. Keep in mind, this is the equation of the vertical asymptote. It's x is equal to negative 3, but x itself is not negative 3. Otherwise, it will be undefined. You can't have a 0 in a denominator. Now, for the inside of the radical, to find the domain, we can set the inside greater than 0, but not equal to 0, because x cannot equal negative 3. So therefore, you can see that x has to be greater than negative 3. If the radical was on top instead of the bottom, then it can equal 0. But if it's on the bottom, it can't equal 0. Now, notice that we have a positive sign, which means that this function will never be negative. Because whenever you take the square root of a number, if the index number is even, it's always going to give a positive result. So now let's graph it. So the vertical asymptote is at negative 3. And do we have a horizontal asymptote for this graph? Notice that it's bottom heavy. Whenever it's bottom heavy, whenever the degree of the denominator is higher than that of the numerator, it's going to be y is equal to 0. Now if we had a plus 5 on the outside, it will be 0 plus 5. So the horizontal asymptote will now be y is equal to 5. But for this one, it's 0. So let's put it on the x-axis. Now, because we have a square root, it's always going to be positive. This function is similar to 1 over x plus 3. If we had the graph 1 over x plus 3, it would look like this. But since we have 1 over the square root of x plus 3, it can never be negative, so we're not going to have anything on this side. Rather, this graph is going to look like this. The shape is going to be similar, but it's going to decrease slower than 1 over x plus 3. The graph 1 over x plus 3 will look more like this. It's going to be closer to the asymptotes. 1 over square root x plus 3 is going to be a little bit further away from the asymptotes. It's going to take a longer time to get to the asymptotes, but the shape, for the most part, is very similar. So now, with this information, what is the domain and the range? Notice that the domain is simply x is greater than negative 3. The function starts at negative 3. That's the lowest x value, and the highest is positive infinity. So the domain is negative 3 to infinity, and it doesn't include negative 3 because that's the vertical asymptote. Now for the range, whenever you have a positive radical, it's going to be 0 to infinity if there's no number on the outside, like a plus 5. Notice that the lowest y value is 0, which is the horizontal asymptote, and the highest goes all the way up to infinity. So the range is from 0 to infinity, but it does include 0 because it never touches or crosses the horizontal asymptote. So that's how you can figure out the domain and range for this particular function. Now what about this one? Y is equal to 2x squared minus x minus 1 over x squared plus 2x minus 3. What is the domain and range for this function? Now the first thing you need to do is you need to factor the expression. So this problem might be a long one. So let's factor the bottom part. So we have a trinomial where the leading coefficient is 1. Let's find two numbers that multiply to negative 3 but add to the middle number 2. This has to be 3 and negative 1. So to factor the bottom part, it's simply going to be x plus 3 times x minus 1. Now for the trinomial on top, the leading coefficient is a 2. So there's going to be some extra work that we need to do. Let's multiply 2 by negative 1. 2 times negative 1 is negative 2. We need two numbers that multiply to negative 2 but add to the middle number, negative 1. This is negative 2 and 1. So we need to replace negative x with negative 2x plus 1x, which we got that from these two numbers. And then we need to factor by grouping. In the first two terms, we need to take out a 2x, and so we'll be left with x minus 1. For the last two terms, it appears that there's nothing to take out, so we're going to take out a 1, and we're going to have x minus 1. If these two are the same, then you're on the right track. In the second fraction, what's on the outside, the 2x and a plus 1, is going to go in the second fraction. So to factor it, it's going to be 2x plus 1 times x minus 1. So now that we have it in its factored form, what is the vertical asymptote in this problem? To find the vertical asymptote, you need to set the denominator equal to 0. But notice that the x minus 1 cancels. So that's not going to be the vertical asymptote if it cancels. The one that doesn't cancel, the x plus 3, is going to be associated with the vertical asymptote. So the vertical asymptote, if you set x plus 3 equal to 0, you'll get x is equal to negative 3. The one that is canceled represents a hole in the graph. So the hole occurs at x is equal to positive 1. Now, what's the horizontal asymptote for the graph? Notice that the degree of the numerator is equal to the degree of the denominator. The highest exponent is 2. So whenever that happens, divide the coefficient of the numerator by the denominator. So 2 over 1 is 2. Therefore, the horizontal asymptote is y is equal to 2. If the degree of the numerator is 1 higher than that of the denominator, you no longer have a horizontal asymptote. Instead, you have a slant or an oblique asymptote. Now, if the numerator is 2 or more units higher than the denominator, then you have no horizontal or slant asymptote. So now we have enough information to graph the expression. So we have the simplified equation 2x plus 1 over x plus 3 if we remove the whole. So we have a horizontal asymptote at 2 and a vertical asymptote at -3. So let's find out where the graph is. Let's plug in a number that's greater than and less than -3, and let's see if it's above or below the horizontal asymptote. So if we plug in -2 for x, what is the value of y? So 2 times -2 plus 1 over -2 plus 3. On top, 2 times -2 is -4 plus 1, that's -3. And on the bottom we have a 1. So we have the point -2 comma -3, which is somewhere over here. Therefore, we're not going to have a curve in this region since the point is over here. So it should look like this. Now for the left side, we need to figure out if the curve is going to be here or if it's going to be like this. So let's plug in another test point. Let's plug in a number that's less than -3. So let's choose -4 for x. So 2 times -4 plus 1 divided by -4 plus 3. 2 times -4, that's -8 plus 1, that's -7. -4 plus 3 is -1, so it's 7. So we have the point -4 comma -7, which is somewhere up here. So therefore, the graph should look like this, based on the points. So now we could find the domain and range. As you can see, all we need to remove for the domain is the vertical asymptote, -3. And we also need to remove the whole. I can't forget about that one, at 1. So that's another thing we have to be careful with this particular problem. So x is 1 somewhere around here. So I'm just going to put an open circle to represent that we do have a hole at 1. So for the domain, we need to remove -3 and 1. So let me make some space. So the domain is going to be from -infinity to -3. As you can see, the lowest x value is -infinity. And then the function is going to stop at -3. Then it starts from -3 again. It's going to stop at 1. And then from 1 to infinity, it's going to start up again. So it's -infinity to -3 union -3 to 1, since we have an open circle at 1, and then union 1 to infinity. So for the domain, make sure you remove the vertical asymptote and any holes from the graph. Now what about the range? For the range, we need to remove the horizontal asymptote, which is y is equal to 2, and we need to remove the y coordinate of the hole. So we got to figure out what the y coordinate of the hole is. So we need to plug in 1 into the surviving equation. That is the 2x plus 1 over x plus 3 equation. So it's going to be 2 times 1 plus 1 over 1 plus 3. So 2 plus 1 is 3, 1 plus 3 is 4. So the hole has the coordinates 1 comma 3/4. So the y value here should be about 3/4. But keep in mind, I just drew a rough sketch. So we need to remove y equals 2 and 3/4 from the range. And keep in mind, the lowest y value is -infinity and the highest is infinity. Therefore, the range is going to be from -infinity to, is it going to be 3/4 or 2? Since 3/4 is less than 2, we're going to reach 3/4 first. So it's -infinity to 3/4, which is here. And then after that, it's going to be 3/4 to 2. So union 3/4 to 2. Then after 2, it's going to go all the way up to infinity. So it's union 2 to infinity. That's the problem with these bigger problems. I'm always running out of space. So if you didn't catch that, here's the range. It's negative infinity to 3/4, union 3/4 to 2, union 2 to infinity. So we remove the y coordinate of the whole and also the horizontal asymptote. We have to take that out from the range. How can we find the domain and range for the function y is equal to the negative absolute value of x minus 3 plus 1? So the first thing we need to do is we need to know, or we need to graph the parent function, absolute value of x, which has a V shape. It looks like this. So now, if we know the shape for that graph, we can graph the transformed function. If you set the inside equal to 0, you'll see that it's going to shift 3 units to the right. And we have a plus 1 on the outside, so the vertical shift is up 1. So the vertex of the graph is at 3, 1. Now notice that there's a negative sign in front of the absolute value. So instead of opening in the upward direction, it's going to open downward. So it's going to look like this. Now with this information, we have enough to graph it. So as the function goes down, it travels to the left. And also, it also goes to the right as well. So x could be anywhere from negative infinity to positive infinity. For an absolute value function, x could be anything. So the domain is going to be negative infinity to infinity if there's no fractions and if there's no radicals. Now the range has limitations. The lowest y value is negative infinity, but the highest y value is 1. So therefore the range is going to be from negative infinity to 1. And since it includes 1, we need a bracket. And so that's how you could find the domain and the range for an absolute value function. Now what about for an exponential function? Let's say if you have the function 2x plus 3 minus 1. Now let's draw the parent function y is equal to 2 to the x. This graph looks like this. This is the generic shape. But for most exponential functions, you could simply plug in points. The points that I would choose will be negative 3 and negative 2 for x. If you're wondering how I got those points, set the exponent, the x plus 3, equal to 0 and 1. If you solve for x, you're going to get negative 3 and negative 2. Now, if you plug in negative 3 for x, negative 3 plus 3 is 0. And anything raised to the 0 power is 1. So 1 minus 1 is 0. So that's why I chose to use negative 3 and negative 2, because I had an exponent of 0, which gave me a nice number, which is 1. Now, if we plug in negative 2 for x, it's going to be 2 to the negative 2 plus 3 minus 1. Negative 2 plus 3 is 1. 2 to the first power is itself, which is 2. And 2 minus 1 is 1. So that's why I chose these values, because I'm going to get two nice values for y. I can avoid any fractions or any large y values. So it's much easier to graph. Now the number on the outside, the negative 1, that's going to be the horizontal asymptote. Exponential functions have horizontal asymptotes, and logarithmic functions have vertical asymptotes. So the horizontal asymptote is y is equal to negative 1. So now let's graph it. So let's plot the horizontal asymptote first. That's where the function is going to start from. And we have the point negative 3, 0, which is over here, and negative 2, 1. So the graph is going to start from the asymptote, and then it's going to increase. So what is the domain and range for this function? The domain for an exponential function is all real numbers. It starts all the way from the left, and it can continue going to the right forever. As it goes to the right, it's going to increase at an increasing rate. So the domain for an exponential function is negative infinity to infinity. Now what about the range? The range for an exponential function has limitations, and it's limited by this number, the horizontal asymptote. So it's going to start from the horizontal asymptote because that's the lowest y value, and it goes all the way to positive infinity because that's the highest y value as it increases. So the range is from -1 to infinity, but it does not include the horizontal asymptote. So now let's move on into a logarithmic function. So let's say if we have log base 2 x minus 3 plus 4. What is the domain and range for this function? A quick and simple method to figure out the domain is to set the inside greater than 0, not equal to 0. Inside a log or a natural log, you cannot have any negative numbers and you can't have a 0 inside. It has to be greater than 0. So just by looking at this, the domain is x is greater than 3, which is 3 to infinity. But we'll prove it with the graph. Now the range for a logarithmic function is all real numbers. That's really all you need to do to figure out the domain and range for a logarithmic function. The range has no restrictions. The domain is restricted, and just set the inside greater than 0 and solve for x. Now to graph it, what you need to do is set the inside equal to 0, 1, and whatever the base is, in this case 2. So this is going to give you the vertical asymptote because we said that you can't have a 0 inside the log because that's where the vertical asymptote will be. So the VA, the vertical asymptote, is x is equal to 3. Now the other 2 points will give us the values that we need for the table. So if x minus 3 is equal to 1, if you add 3 to both sides, x will be 4. And if x minus 3 is equal to 2, x is 5. So now let's calculate the y values. If we plug in, or if we substitute x for 4, we're going to have log base 2, 4 minus 3 plus 4. 4 minus 3 is 1. Log base 1 is always 0, regardless of what the base is, because 2 to the 0 power is 1. So it's 0 plus 4. The first point is at 4. Now for the next one, let's plug in, well, let's substitute 5 for x. So log base 2, 5 minus 3. 5 minus 3 is 2. Log base 2 of 2 is 1 because 2 to the first power is 2. So it's 1 plus 4, it's 5. So now let's graph it. So we have a vertical asymptote at x equal 3. And we have the point 4 comma 4, which is over here, and 5 comma 5. So for a logarithmic function, the graph starts at the vertical asymptote, and then it's going to follow the 2 points. So it's going to look something like that. Whereas for an exponential function, it starts from a horizontal asymptote. So as we can see, the lowest x value is 3, the highest is infinity. So the domain is from 3 to infinity. As we said before, x is indeed greater than 3. Now for the range, the lowest y value is negative infinity, but this keeps going up forever. So for a logarithmic function, y has no limitations. So the range is negative infinity to infinity. So now let's see if we can summarize logarithmic and exponential functions. So the generic graph 2 to the x, it has the horizontal asymptote at y equals 0, and it's an increasing function. Now the graph y is equal to log 2 of x is going to have a vertical asymptote at 0, and it too is an increasing function. So this is log, and this is 2 to the x. So as you can see, an exponential function, it increases at an increasing rate, whereas a logarithmic function, it increases at a decreasing rate. Now, exponential functions, they have horizontal asymptotes, which means that the range is restricted. You have to remove the horizontal asymptote if you want to write the range. Now, for a logarithmic function, it has a vertical asymptote, which means that the domain for a log function is restricted. So for exponential functions, the domain is always negative infinity to infinity. But for a logarithmic function, the range is always negative infinity to infinity. Now, the range for an exponential function, it's going to start from 0 and go to infinity, since the horizontal asymptote is y is equal to 0. Now, if it's different, then this number is going to be different. So if there was a plus 3, the range would now be 3 to infinity, if it's increasing. Now keep in mind, if you have a negative sign in front, it's going to flip or reflect over the x-axis, so it's going to be decreasing. And so in that case, the range will be negative infinity to 0, as opposed to 0 to infinity. Now for the log function, it has a vertical asymptote, so the domain is restricted. So the domain is going to be from 0 to infinity. Now, if you have a negative x on the inside, it's going to reflect over the y-axis, so it's going to look like this. In that case, the domain will be negative infinity to 0, so be careful with reflections and transformations. Now let's go over trigonometric functions. What is the domain and range for sine x? The graph of sine looks like this. Sine starts at the center, it goes up, and then it goes down. The amplitude is 1, so it varies between 1 and negative 1. Now the sine wave, it continues forever. It goes both ways. So the domain for the trigonometric functions for sine and cosine is always going to be negative infinity to infinity. However, the range has limitations. The range is based on the amplitude, or the y values. So the lowest y value is negative 1, and the highest is 1. So for cosine, the situation is the same. Cosine starts at the top, so it looks like this, but it can keep going. But the amplitude is 1, it's going to vary from 1 to negative 1. The domain for a cosine wave is always going to be negative infinity to infinity. That's going to be the same. The range in this case is also negative 1 to 1. Now sometimes you may have a vertical shift, and the amplitude might be different. Let's say if you have 3 or negative 3 sine x, let's make it positive 3 for now. Positive 3 sine x plus 2. So the graph shifts 2 units upward. So the center is going to be at 2. Now the amplitude is 3. So it's going to be 3 units above the center line, which has a maximum value of 5, and 3 units below. So the sine wave is going to vary from negative 1 to 5. Now the shape is going to be the same, and it's going to continue going on forever. So as you can see, the domain is still from negative infinity to infinity, but the range is now negative 1 to 5, and it includes those points. So here's how you can find the values for the range. Start with this number. It's going to be 2 plus 3. That's going to give you the upper limit, which is 5, and 2 minus 3 will give you the lower limit, which is negative 1. Let's try another example. Y is equal to, let's say, negative 4 sine x plus 3. So the vertical shift is 3. So the center, or the midpoint line, is going to be at y is equal to 3. Now, the amplitude is 4. Amplitude is always a positive number. But to find the upper limit, we're going to add 4 to 3, which will give us 7. And to find the lower limit, we're going to subtract 4 from 3. So that's going to give us -1. Now, positive sign, it starts at the center, then it goes up. But negative sign starts at the center, and then it goes down. And as you can see, the domain is going to be negative infinity to infinity, because the sine wave will keep on going in both directions forever. The range, though, is based on these numbers. So the lowest y value is -1, the highest is 7. So that's how you can find the domain and range for a sine or a cosine function. Now the next thing we need to talk about is the tangent function. Tangent has a restricted domain, but the range is unlimited. Tangent has a vertical asymptote at -π/2 and at π/2. And at 3π/2. And at -3π/2. It has many vertical asymptotes. The period is the distance between the two vertical asymptotes for a tan or cotan function. The period is 2π/b, where b is the number in front of x. So b is 1 in this case. Well, actually, let's take that back. For a sine and cosine wave, the period is 2π/b. But for a tangent wave, or a cotan wave, it's π/b. So b is 1, so it's just pi, which is the difference between π/2 and 3π/2. Now the tangent function is an increasing function. It looks like this. That's positive tan. Negative tan looks like this. As you can see, it can go all the way from -infinity to infinity on the y-axis. So therefore, the range is unlimited for a tangent or a cotangent function. However, the domain is everything except the vertical asymptotes, which is going to be difficult to write in interval notation. So, however you want to write it, I'll leave it up to you, but you need to remove the vertical asymptotes from the domain. So, that is it for this video. We've covered most of the topics that you'll see in regards to domain and range. So hopefully you found this video to be helpful, and thanks for watching, and have a great day.